Hello everyone. Have you ever noticed how a swing at the park moves higher and higher if you push it at just the right time? That's resonance. It's not just a fancy physics word, it's a real phenomenon we experience every day. Resonance occurs when the frequency of an applied force equals the natural frequency of a system, making the vibrations grow dramatically. Today, we'll see examples of resonance in pendulums, machines, musical instruments, and even air columns. Let's start with pendulums, classic physics toys. Imagine two identical pendulums hanging side by side from a rubber string. If you set one in motion, the other starts swinging too, without you even touching it. Why? Because they both have the same natural frequency and energy is transferred through the support. The second pendulum resonates with the first and starts swinging with large amplitude. That's resonance in action, energy hopping across like a secret handshake between twins. Now, let's move to machines. Ever been in a bus or car and suddenly heard a rattling noise at certain speeds? That's resonance again. The piston in an engine moves to and fro, and if its frequency matches the natural frequency of some loose part in the vehicle, that part starts vibrating like crazy. This resonance causes the rattling sound. Engineers hate this kind of resonance because if it's not controlled, it can shake parts loose or even damage machines. So yes, resonance can be useful, but it can also be noisy and dangerous. Let's make things musical. Take a guitar string. If you pluck it in the open air, the sound is faint. But put that string over a hollow sound box, and suddenly the music is loud and clear. Why? Because the air inside the box has the same natural frequency as the string, and resonance boosts the sound. The sound box acts like a megaphone, making a small vibration turn into a concert-ready performance. Without resonance, musical instruments would whisper instead of sing. Before we go further, let's quickly compare forced and resonant vibrations. In forced vibrations, the applied frequency is different from the natural frequency, so amplitude stays small. In resonant vibrations, the applied frequency equals the natural frequency and amplitude becomes very large. Think of it like dancing. If the music doesn't match your rhythm, you move awkwardly. But when the beat matches your natural groove, you dance with energy and style. That's resonance. Here's a classic experiment with a tuning fork and a tube. Strike a tuning fork and hold it above a tube filled with water. As you lower the water level, the air column inside gets longer, changing its frequency. At certain lengths, the natural frequency of the air column matches the tuning fork. Suddenly, a loud sound bursts out, resonance. Lower the water further, and the sound fades, but at another specific length, often 3 times the original, the loud resonance appears again. It's like the tube and fork are singing in harmony. Let's wrap up. Resonance is not just theory, it's everywhere. From pendulums swinging in sync, to rattling car parts, to loud guitar notes, to air columns humming with forks, resonance shows how powerful frequency matching can be. Sometimes it's helpful, like amplifying music, and sometimes harmful, like damaging machines. But the central idea is simple. When applied frequency equals natural frequency, vibrations grow with large amplitude. That's the magic and danger of resonance.